Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. Today we're going to talk about a real quick question here associated with fluid flow and static fluids kind of together. So just to describe the situation for you, we have this system here where there's this tank of fluid down here, right? That if this system wasn't here, if it was just all open to the air, right? Just to draw that real quick, right? If we didn't have the system set up, those tubes would all be the same size. They'd all be connected to this tank down here, and the fluid inside of them would all be, since they're all exposed to the air pressure, right, the same air pressure, they would all be at the same level, right? But here in this system, we have kind of like something that's making the airflow different. There's a fan kind of pulling the air this way, and based off the area here, the air is kind of going to be flowing different versus the one tube that we do have that is just experiencing the air pressure due to the atmosphere itself. So what we know is that based off how the fluid flows, that's going to affect how the air pressure pushes down on the fluid. So what we kind of know is that in the larger areas, right, where here the area is infinite, right, it's just out in the environment, so the area is the largest here, right, or in these larger areas, we see that the air or fluid flow, the fluid isn't flowing through here, but we think of air as fluid. This is just the concept. The air or fluid will move slower, right, the larger the area. The smaller the area, right, that the air or fluid's flowing through. Again, this is the water down here isn't flowing, so it's the air that's flowing here. So we're really looking at the air here. But the air or fluid will move faster in a smaller area, right? So in these smaller areas compared to these larger areas, the air will be moving faster. And that's what's important to know here, because we know some things about that fluid flow, right? We know that the faster the flowing, right, here we're talking about faster and slower. And here we say the faster the flowing fluid or air, here we're talking about air because the fluid isn't flowing here, the air is flowing, right? The faster flowing the air or fluid, the less pressure or force it applies to the environment, okay? So when the air is flowing, the faster it's flowing, right? The faster the fluid or air is flowing, the less pressure or force it applies to the environment. So the faster the air flows here, the less force it's going to be putting on these tubes and on the water. That's what this is saying, right? And the slower flowing the air or fluid, the more pressure or force it applies to the environment. So the larger the area, the slower the air is going to flow, the more pressure it's going to apply to the fluid in these tubes and its environment, right? That's what this means. So again, faster flowing fluid or air, the less pressure or force it applies to the environment. Slower flowing fluid or air, the more pressure or force it applies to the environment. And what did we say up here? The smaller the area, the faster the air is going to be flowing, right? So the air is going to be moving faster in a smaller area. That means it's going to what? Apply less pressure or force to its environment versus air flowing, right, in a larger area, which is going to be slower. And that slower and flowing air will apply more pressure or force to its environment, or in this case, this fluid in these tubes. Okay? The other thing just to keep in mind here that we're saying right here is that static fluid, the static fluid in these tubes, the only time it experiences a change in pressure, right, is due to either depth, right? So in a static fluid, right, static fluids, they have a change in pressure either due to depth, how deep you go in the fluid, right? Or they have a change in pressure due to some force being applied to the container it's in, right? If you apply a force to one part of the container, that force or pressure is applied to the whole container, right? So that's what's going on here. So as these start to press on each other, right, there's going to be somewhat of a change in pressure, but it'll be equal because they'll be pressing on each other. So just know static fluid experiences different changes in pressure than fluid flow. We're trying to talk about in this question how the fluid flow is going to apply pressure, right, because it's the air that's flowing. The static fluid isn't going to have a change in pressure. And as we know, don't forget that we talked about in our concept video, the change in pressure is net force, right? That's what we're trying to say, right? So there's not really any net force here, right? Unless it's due to depth or some applied force to some part of the container. where fluid flow can have a net force, right? You can apply a net force to something based off how fast or slow it's moving. That's what we're trying to say. So that's the difference between fluid flow and static fluid, right? Fluid flow, static fluid. So here, right, we've already kind of explained it, right? But here we see that since this tube's just exposed to the open air, the air is pretty much just static, right? It's just kind of sitting there unless there's a wind or a gust to come along. It might blow the air above this tube and make it move a little bit. But we're assuming that this is just out into the atmospheric air, just being exposed to the air, so everything is just static. So the velocity of the air right here is maybe very small, if not moving at all. So we say it's the slowest flowing air here, right? And if we know it's the slowest flowing air, we can also say it's going to be the largest force applied to the fluid. That's something we know, right? But we'll come back to that. Okay, here we see this is the smallest area, right? The fan's pulling the air through this part, right? And here this is the smallest area. We know small area means faster fluid flow. So if this is the smallest area, that means the air is going to be moving the fastest out of these four tubes. The air above this tube will be moving the fastest versus the air above this tube, which will be moving the slowest, right? And then we see with these two, right, the areas are pretty close to each other, but this one has a little bit larger area than this one. So if this has a larger area, that means the velocity is going to be slower than this one, but faster than this one out here, because this is our slowest flowing one, right? So it'll be our second slowest one, right? The air in this area that will be flowing the second slowest, versus this one, right, is going to be flowing faster than the air in this area, but it's going to be moving slower than the air in this area, right? So the air above this tube, right, will be moving faster than the air above this tube, but slower than these two. And the air above this tube, right, will be moving faster than these two, but slower than this one, okay? Because it's kind of hard to describe these in terms of tubes, right? And we have this labeled as tube 1, this labeled as tube 2, this labeled as tube 3, and this labeled as tube 4. All right, so we know tube 1 has the slowest flowing air, but the largest force on the fluid. We know that 2 has the fastest flowing air, which means by concept, right, should be applying the smallest force on the fluid when compared to all four of these, since it's the fastest flowing air there. So we can kind of say that right there, and that's what we want to know. So we can kind of look at this and already kind of draw the levels here, right? Because the question is, what is the water levels going to look like in this system, right, when we set this type of thing up above these tubes, right? When they're just exposed to open air, they'll all be the same level, but when the air flows different above the tubes, that air applies different pressure and we get different levels, right? So here we see for 3 and 4, right? Again, we understand 1 and 2 what's going on. This is the highest level in the tube because it's the fastest flowing air, which means there's going to be less force from the air. And we could also draw vectors here. This would be the smallest vector. This should be the right. That's our force vector. So that's going to be the largest force, right? That's going to be the smallest force. This is going to be the next to smallest force, right? So larger than this one, right? We draw that a little bit better, right? But not so much larger. And this one, right? You can see. So in terms of force vector, you see this is the largest. This is next to largest. This is next to smallest, and this is the smallest, right? So we can see that, you know, that's what we're saying down here, and that's what we've been saying. Okay, but here with 3 and 4, pipes 3 and 4, right, we see that the airflow over here is smaller compared to the airflow over here, which means that if the airflow above here is smaller than it is above here, that means the pressure is going to be greater for tube 3 than it is going to be for tube 1, which means the level is going to be smaller for tube 3 than tube 4 when comparing those two. All right, so when we look at the whole system, let's just go back and make sure that we understand, because it's a little weird to say. It's hard to say these because they sit right in the middle, right? But we know that these two are the extremes, right? So we know, right, that in terms of height, level height, right, we know that 1 1 is going to be smallest, right? And then 3 is going to be smaller than 4, which is going to be smaller than 2. Okay, so this is what we're saying in terms of level, water height. Okay, 1's going to be the smallest, 3's going to be the next smallest, right? Or however you want to think about it, the next largest. I don't want to think about it, right? But 1's the smallest. Right, so if we do this, let me kind of erase these to give some orientation here. But right, if this is 1, this is 2, this is 3, and this is 4, right? Then we're saying in terms of water level, okay, we can see that 1's going to be the smallest, 3 is going to be the next smallest, 4 is going to be the next largest, and 2 is going to be the highest, right? Or we could write that in reverse order, right? Where 2 is the greatest, right? 4 is going to be smaller than 2 but greater than 3, and 1 is going to be smaller than, or 3 is going to be greater than 1 but smaller than 4, right? So this is another way to look at the water level that we're trying to determine. Okay, so we can either order the water level in terms of smaller to greatest. That's what this one's doing. This is smallest, or lowest, sorry, not smallest, lowest water level to the highest water level, right? Where 1's our lowest water level, 2's our highest. Or this one's labeling, right, from highest water level. Oops. To lowest. Okay. So this one's doing highest water level to lowest water level, right? This is 2's the highest, 1's the lowest. This one's looking at it the opposite way, from lowest water level to highest water level. Okay. So again, we discussed why. This is a very short video. It's just to make sure that you understand the concepts here. But if you're not too sure what's going on here, rewind, rewatch this video, make sure that you understand the concepts of what we're saying here and how these match up. We're just saying the same thing two different ways. Again, this is from lowest to highest. This one's from highest to lowest water level. The question was just trying to look at what these water levels would be with this system with the air flowing through. All right? So thank you so much for watching. I hope this was helpful. Remember, talk to your professor, talk to your tutors. If you have SI, make sure you're going to those things, get the help that you need, and I'll see you in the next video.